Hello and welcome to podcast, aka Toddcast, number 29. So continuing on with nucleophilicity and electrophilicity and therefore nucleophilic substitution, I want to start by actually coming up with an analogy that if we understand how this works, it'll help us with a bigger picture. And so in this scenario, you very much want a seat. And there's a bench, holds four people, and because there's already four people on it, it's like, dang it, there's no open space. I can't sit down on this bench. And it's the best bench in the whole world. I mean, there is no better bench. So everybody wants to sit on it. So you have a couple choices. Option number one, you can wait patiently till somebody leaves. That's a nice way to do it. We'll say that's sit nice version number one, SN1. And then the other thing you can do is just start pushing somebody off. And again, to push them off, you still believe in conservation momentum. You want to push them from behind. So if you come in from behind, you knock them out in forward direction, seat opens up, you take it, you're set. So that's not a nice version. So let's make that option number two, sit nice version number two, SN2. So the question is just going to come down to, do you push your way in, force the out person off, like option two, or do you patiently wait until somebody leaves? Okay, so you have some decisions to make. And in that decision are the factors involved. So amongst them, the size of the people on the bench. If you're small and they're really large, you're not going to have much luck pushing them off, or even squeezing in between them or whatever it takes. Equally, if they're tiny and frail and, I don't know, easily pushed around because you're a bully, then you can push your way on and get your seat pretty easily. So the size of the people on the bench will play a role. And so a couple things that you consider. First off, is somebody leaving? How much you want to see? And then probably most important, how crowded is it? And there is always some sort of peer pressure. Like if your friend's saying, do it, push them off, you can do it. Might entice you to do that method, sit nice too. Or if they say, no, be polite, have your manners, wait till somebody leaves, that might entice you to sit nice version one. So the things that influence your decision, is anybody leaving? How much do you really want to sit down? Is it worth pushing your way on, or might as well wait? How crowded is it? So well, can I even push my way on if I wanted to? And then the influence of your surroundings. All these things are going to play a role. Okay, so that's beforehand. So decision-making processes. If the crowd on the bench is really big, if it's very crowded, they're shoulder to shoulder, there's hardly any room, you might want to wait. But if they're small, you might want to force your way on. Equally, other things to consider during it, once you are pushing your way on, something to consider. When you're pushing your way on, for a brief moment, there'll be five people on the bench. So the four that are there plus you, but the reality is you won't be all the way on, and the person going off won't be all the way off. You're kind of half on, half off. So I'm going to refer to this process as mono-cheeking, where you're only partway on the bench and they're partway on the bench. So although there are five people on the bench, two are kind of half on, half off. Okay. Equally, if somebody moves, leaves the bench, opens a spot, before you sit down, there's only three people on the bench. So during the process, if you force your way on, there'll be five, and if you wait, there'll be three. If there are five, that's still so crowded, there's no way people can move around. But if there's only three, then they can move around. So somebody, let's say, left from the second space over left to right, the person third over can move and take their spot and leave the opening where they were, or somebody at the end can move in that middle space and leave an opening. So in other words, if there's an opening, so if only three people are on the bench that can hold four, they can move around. So whether you get that spot or not will be open to like just how fast you can get there. They can move around faster than you can run in and get the seat. So there will be some moving around. You may have to choose your seat accordingly. And then, as mentioned, is anybody mono-cheeking? Are they basically only half on the bench, including you, the nucleophile? Okay, so if they leave first, or if you slide in, if they leave first, then there are three on the bench, as mentioned, and if you slide in, there's going to be five on the bench. But again, two of the five are kind of half on, half off. Finally, afterwards, when everything's said and done, you can predict how the results are going to go, or the chaos of the way they're going to go. So in the event that you like force your way on, do you have any impact on your rate? So in other words, the more you force your way on, can you get that seat sooner? Whereas if you patiently wait, if you do option number one, you wait around, you can't sit down until the leaving group has left, until that person has left the bench. So you have no control over your rate. So the rate only depends on when that person leaves. As mentioned before, if it's 5 people on the bench, it's very predictable. You're going to push your way on, they're going to go off, so you know exactly where your spot is going to be. Whereas if the person leaves first, like we mentioned here, they can move around. So the order of people on the bench can fluctuate. Who knows what order it'll be by the time you finally get that seat. And then finally, fast or slow. As mentioned, if you push your way on, you get that seat soon. If you wait, it's very slow. You might take, I don't know, 10 minutes, 20 minutes, an hour. You have no control over when you'll sit down. Okay, this analogy, although you're probably sitting there thinking, gosh, there's no way that's like a carbon with 4 things on it, and steric hindrance, meaning how big everything is, how crowded it is, and whether the leaving group leaves first and then or the nucleophile goes on, or whether the nucleophile goes on and pushes it off, you're probably not even seeing any correlation. But believe it or not, there is a near perfect correlation between this scenario. So a few things to consider: leaving group leaving, and the nucleophile, how good of a nucleophile it is, if the electrophile is crowded or not, and then peer pressure solvent effects. So a good example, fluorine, it's an okay nucleophile. It's not great, and we have it on the like good bad cusp on that line. But what really matters is what solvent it's in. So if we were to put it into a protic solvent, one that forms hydrogen bonds, we know NOF, the 3 atoms that form hydrogen bonds, in that protic solvent, F will be bound by a solvent. So it won't just be moving on its own. It's going to be dragging all that solvent with it. So it's going to be a terrible leaving group because its peer group, its peers are clinging to it. But in an aprotic solvent, where nothing's clinging to it, it's going to be free to move in and it'll be a better nucleophile. So the solvent can help the nucleophile to come in hindered or unhindered, and it can also help pull the leaving group off. So if the leaving group is in a polar protic environment, hydrogen bonding environment, it can help pull the leaving group off and stabilize the carbocation results. And so that actually can help. So the solvent, the peer pressure, the environment will also influence it. So we'll get into these as we go, but hopefully this analogy seems reasonable. So let's see how it will actually look when we go through it. So if they leave then sit, slower process. If you push them off, fast process. Okay, so this analogy really hopefully will help you visualize what's going on. So I want to start with the SN2, option number 2, the not so nice method. This is one where we push our way on. The faster one, the one that requires smaller things, smaller groups, smaller substituents on the carbon we're attacking. So the reaction requires that the nucleophile attack the electrophile from the backside. So again, conservation of momentum, and also it wants to go on the side that's positive, not negative. It'll gradually push the leaving group off. It isn't just you hit it and it bumps off. You have to sit there and push it off, while simultaneously it forms a bond. So we'll look at this very carefully in slow motion here. So the nucleophile is going to line up the electrophile. It has to be aligned the right way. So notice this is right here. It can come in from the backside and kick this out. So here's my nucleophile. Here's my leaving group. This whole thing is my electrophile. Notice I have a carbon that has a methyl, ethyl, and an H. H is small, methyl's medium, and ethyl's big. So this is kind of one of those confusing ones. Maybe it's big, maybe it's small. So I can't really decide from its size what it's going to do, whether it's going to push on or wait. And that's one of the things that's going to be a little bit challenging about this, is making a decision whether it's SN1 or SN2. Okay. Once it goes in, the electron density is going to shift. So these electrons are going to now be shared here. So instead of being localized on this carbon, they're going to be shared between the 2 atoms in a sigma bond. And these electrons are going to start to move towards bromine. So it's going to go across. Notice the dash bonds are very much like the term monocheeking. It's not a full bond, it's a partial bond. And notice they are aligned perfectly because the orbital has to be lined up. It's got to be backside attack. So that's going to go there and that's going to go there. The one thing of interest is my negative charge is no longer on here, it's partly on there. So it's partly negative. And the bromine, which is getting electrons, is also partly negative. So you got a partial negative on carbon, partial negative on bromine. I might as well put those in just to make note. So that negative charge is accounted for, but across 2 different atoms. Then finally, the leaving group completely leaves. So this is going to go off. This one becomes a solid bond. So there's my actual covalent bond. The minus is now shifted all the way from where it started on C to on bromine where it finishes. So again, the things of interest. Bromine is my leaving group, check. Cyano group is my nucleophile. Carbon's a better, less electronegative atom, so it's a better nucleophile of the two atoms. And then the electrophile is the whole thing. Okay, so practice with this will help, but just make sure we have all the rules. I want to reiterate them over and over and over. So when this one pushes its way on and pushes the BR off, it's said to happen in one concerted step. One thing that I have made an error on, and I hope I have it corrected by the time you see this in class, is notice this was ethyl, methyl, and H, methyl, and ethyl. So I should correct this and make sure that I have all the right things still on there. Okay, so everything gets pushed over. So the CH3 was in front on the left, now it gets pushed to the right, but stays in front. The ethyl, which was in the plane on the left, now is on the plane on the right. And the H is now in back. So those are those little unnerving things that it was a typo by me when I made these slides. But hopefully you can still see that it comes in and kicks out. And it just goes to show you how important that part of the reaction is, and how I could have gone through these slides multiple times and didn't even notice that I'd messed that one up because I'm so focused on this going on and that coming off. Because that's basically what happens. Once you make a decision, it's going to be SN2, this matter just pushing its way on and going through. It occurs in one step, and you can visualize it as follows. So this is one of those things that hopefully helps the visualization process. I have the same three groups here, I have my BR, but I switched from a mode of just writing what everything is to now hopefully animating it, making it clear. Again, this is my electrophile, BR is my leaving group. CN was my nucleophile. I'm not going to have the triple bond, I'm just going to draw it like this. And as this occurs then, so this has to come in from the backside and push its way on. So as it comes in, the nucleophile is going to work its way in. I'm going to follow an energy diagram. So my energy is going to start somewhere around here. It's going to go up and finish where it does. So I'm going to call this, let's say, the starting material, what we have here, 0.1. And then when it pushes its way in, here's 0.1. It's going to go to about here. I want to show this part of the diagram first. So notice that it has pushed its way on. When it did, these three groups, the H, the CH3, and the CH2, CH3, the ethyl, notice they rotated up a little bit because now they're being crowded out by this group coming in. And as this one leaves, there's less crowding, so they're free to move over. So it's going to actually rehybridize or reform as this process occurs. Notice also, it's still early, so this bond is long, this one's short. So the BR is on more than the CN is on. But I'm right around here, 0.2. Okay. Also note, as before, we have a delta minus and a delta minus. Notice my delta minus is a little bit bigger on the CN than it is on the BR. Just to emphasize that, again, this isn't as bonded as this one is. But electron density is moving over, so electron density is going to move over. As this one moves further in, you should expect these groups to continue moving away to get out of the way. So there they go. As they come over, I now have this being roughly equal in bond length, roughly equal in charge, so hopefully the size of these seems comparable. And I'm now at this point, known as a transition state. I cannot measure it, I can't fully observe it, but I know it has to happen because I know if this thing is coming on from the left and this is leaving from the right, there has to be some point where they're both equally on and off, they're both monocheeking equally, and that these groups are forced into a plane. So it's kind of hard to see, but the CH3 is eclipsing the H from my straight on view. Okay, if we look at this, now it's going to come back down in energy, meaning it's going to go from the strained 5-membered system where you have steric hindrance of everything to pushing the BR off. So we go a little bit more in the forward direction. There's transition state. Number 3, it's going to push forward. So we watch as it moves over. So now the CN is on more, and it's crowding these to the right and pushing the BR off. So we're moving down to around there. And then finally, as it pushes all the way on, these will go to their normal state, 109.5 bond angle, and BR is completely off. So BR is gone, it's now a full negative on the BR, and I have a new molecule. Okay, what we just witnessed in awesome Macintosh animation was something called backside attack, This came in from the backside and kicked the BR out the front side. But we also noticed that the inversion of this chiral center here, it went from on this side on the left to middle to the right. So an umbrella, like an umbrella blowing in the wind, it turns inside out on itself. And so if I were to go back and figure out what the chirality was in the beginning, it would be the opposite of what I have here. So let me go ahead and figure this one out. So there's 4, 3, 2, and 1. H is in back. So if I take my priority, 1, 2, 3, this is an R center. But in the beginning, with the BR on the other side, the priorities would have been 1, 2, 3, and 4 in back. So it would have started S. So it goes from S to R. Inversion of chirality. That, with all we did about learning R and S, and probably at some point you had to ask, why are we doing it? This is why. Because the chirality inverted, it shows us that it must have gone this way. It must have been something coming in, pushing the backside and turning it inside out, kicking the BR out the opposite side. Okay, that is my SN2 reaction. This is now my product. This is now my leaving group. So the nucleophile is now part of the compound that used to be electrophile and acts as a product. The leaving group is now free to go wherever it's going to go. Energy diagram is this way because I had a weak bond to BR to begin with, and now I have a much stronger bond, carbon to carbon. So I broke weak bonds to form stronger bonds. So small number minus big number is going to be negative, meaning it goes down in energetics. The delta H, I understand. The delta S, 2 molecules, probably not a big change in entropy. So delta G is pretty much equal to what delta H would be. So breaking a weak bond to form a stronger bond is going to be downhill. So I'm feeling pretty good about this. It's combining all the stuff we looked at before, a little bit of R and S, a little bit of steric hindrance, a little bit of energy diagram. So everything we did in those first few chapters were to build up to be able to understand this a little bit better. Okay, so energy diagram, again, this is my starting material. And notice that it is, as mentioned before, 1, 2, 3, H and back, so that is S. The product, 1, 2, 3, H and back, so it is R. So it underwent inversion of chirality. It was a predictable result. So that is one mechanism. So what are the things that matter in this reaction? So a couple of things to consider before. So we're going to do the same thing we just did with the bench analogy, but now applied to this structure. This carbon, as I mentioned before, has something small in H, something medium in methyl, and something large in ethyl. So it's kind of large, but kind of small, so I don't really know. So I should be considering how crowded the electrophile is. It's a secondary carbon, so could go either way. So I'm going to give this a question mark. It's a good nucleophile. Carbon doesn't really want a negative, so it's going to share electrons. And then solvent, to make this go, if it's a protic solvent, hydrogen bonds, it might hinder this reagent from coming in, this reactant. But I still need some sort of polarity to allow the negative to transfer over. So typically we use what's known as an aprotic, cannot hydrogen bond, polar solvent. So things like acetone, like a carbonyl of some sort is useful. Ethers can be useful. You're going to see the solvent called THF frequently. So I'll just toss that in here. This is an ether, but it's a cyclic ether, so it's a little bit, well, it's just cyclic, so it's stability is a little bit higher, but it's an ether, O bonded to 2 R groups. So it's polar slightly, and it's aprotic. No hydrogens on this, they're all on carbon, can hydrogen bond. So it's not going to hinder the nucleophile, but it will facilitate transfer of charge. Okay. The during part, notice we have 1, 2, 3, 4, 5. 3 real bonds, 2 monocheekers. So 5 ligands or 5 atoms attached to the central carbon. There are partial bonds. This one is partly on, this is partly off. So I love that phrase. 2 people monocheeking. Kind of on, kind of off. So kind of on the bench, kind of falling off the bench. Afterwards, inversion of chirality. We went from an S center to an R center. Now, one thing to make note of, if when you substitute, your priorities change. So we were lucky that the nucleophile ended up being priority number 1, and the leaving group used to be priority number 1. So it's easy to see R to S or S to R. but you still get the inversion. But if the chiral centers change priority for some reason, then you may not see it in R and S as obviously. You should see it in terms of the overall chirality, but you may not see it in the traditional R and S form. Fast or slow? Well, if it's SN2, it's going to go very fast. SN1 is going to go very slow. Because we did a good nucleophile, and because secondary isn't that crowded, and with the right solvent, we will see this come in and do its thing. Okay, so feeling pretty good about this one. The rate, because it is SN2, depends on the nucleophile concentration. So the more of this add in, the more chance it has to collide and carry the reaction forward. But also depends on the electrophile. You have to have something to attack. So the rate's going to depend on both. So if I double the nucleophile concentration, rate doubles. If I double electrophile concentration, rate doubles. They both depend, the rate depends on both electrophile and nucleophile. Excuse me, so sorry. So let's do some examples, see how it goes. So I want to do my consideration, my before, during, and after. So before, I'm going to notice that this carbon has only one other carbon on it. It's primary. So is it crowded electrophile? Nope, primary, so no. Okay, what about the nucleophile? Nucleophile is a really good one. So ammonia, I'm gonna put it in the good category. It's where it showed up previous list. It's an SN2 reaction, so that tells me what it's going to be. So consider things after. I'm not going to do the monocheekings anymore. That was cute and all that, but now I want to consider what's going to happen in the end. Inversion of chirality, except this has no chiral center, so we can't really prove it, but it still is going to come in from the left, kick the iodine out to the right. So chiral inversion. It's not chiral, so we can't tell, but I'm still going to show it as inverted. I'm going to show those groups moving over as it came in from the left and kick the I out to the right. Fast or slow? SN2 reactions are very fast because you're not waiting for somebody to leave. You're sort of influencing the pathway. Okay, so let's consider this next reaction. Excellent nucleophile with a negative is one of the best. And this carbon right here, a little bit tricky, but there's one carbon here, and an H here. So it's bonded to two other carbons. So consider before, is it crowded? Oh, that's open to debate, because the reality is it's only secondary, but secondary can be crowded if this thing's big enough. So I'm going to give it a question mark. It's secondary, so is it crowded, is it not? So we're going to say for sure tertiary is crowded, for sure primary is not crowded, and for secondary it's going to be well, let's look at some other factors. Good nucleophile, excellent nucleophile, one of the best. So CH3 is small enough, it's a sulfide, so we're good. So that's going to definitely want to come in. Has to be from backside attack because it's an SN2. So just note, it's going to have to come in from this direction. And I'm going to actually redraw this, and although it's kind of anal, I just want to emphasize it's actually coming in perspective-wise behind the CH3, so I should do that. It's coming in like that, and it's going to knock the BR out. So actually, let me make a prettier circle. Okay. Afterwards, chiral inversion, you bet. This is a chiral center, so if you want to do your R and S configuration, you should come up with thumb pointing direction number 4, fingers start at 1, and that it would be a right hand going from 1 to this front one to the back one, 1, 2, 3. So R in the beginning, and in the end, your H, which used to be here, has been forced up. So priority 1, 2, 3, put your thumb up, it's now left. So it went from R to S. Okay, so I know it had chiral inversion at the reactive center. And was it fast or slow? Because it's forcing its way on and not waiting around, it's going to be fast. However, it will not be as fast as this first one because primary is going to be easier to attack than secondary. But it is still an SN2 reaction. This is one of the things you're going to have to be able to do is predict whether it's an SN2 or an SN1 reaction. And we're going to pile on a few more things by the end of this chapter. But for now, SN2 and SN1 is going to be my comparison. SN2 means it depends on two things, or there are two things coming together for the reaction. Nucleophile has to come in to kick the leaving group out. Okay, the SN1 is the less kind one. Choose that word. It's one where the group must leave first. So it completely leaves, and it leaves behind a carbocation. So here's my original molecule. Notice it's now tertiary. So like we mentioned, primary will go by SN2, tertiary will go by SN1, secondary will depend on what the world is around it. So for this one, this has to go by SN1 because the nucleophile just cannot fit in this narrow space here. So the leaving group has to leave first to form a carbocation. So when this leaves, what we mean by carbocation is a cation, a plus charge located on carbon. Clever name. So I'll get rid of my arrow because the blue one's so much prettier. This carbocation, notice it's now planar. So a few things to note, it's sp2 hybridized because it has 3 bonds in an empty p orbital. So this is, again, why some of the things we did early in the semester were so critical to be able to build the foundation to understand what we mean by a carbocation in sp2. sp2, 120 bond angle, that's well and good, but the most important thing, trigonal planar. So because this is planar, there's no favored side. Left and right are equally accessible. So after the leaving group leaves and you form a carbocation, the nucleophile comes in. The nucleophile is free to come in from the left side and force everything to the right, or come in from the right and force everything to the left. There is no preference one way or the other. So it's 50-50. It's free to attack the positive carbon, positive charged carbon from either side, left or right, as this is drawn. So from the left, if it came in, let me get rid of the sp2. So from the left, it's going to come in, it's going to attack and form that. So notice this is on the left side and force the other groups to the right. And I should put, it's a lone pair. But not absolutely, I mean, it is critical. I should have had that, but hopefully you just get the idea. It's something coming in from the sulfur. Or it could come in from the right. It could also come in this way, where it comes in and attacks to the right and forces these groups the other direction. So these are not chiral centers because the CH3s are equal, but if these 3 R groups, these 3 carbon chains were all different, then one would be R and one would be S, depending on what the priority is. It would vary, but let's say this one was R, this would have been S, or let's say this was S, the other one would have been R. Meaning this gives you equal parts, so it would give you a racemic mixture if it was a chiral center. Okay, so a couple of things to really cling to on this one. Number one, it's 2 steps. It first leaves, then the nucleophile comes in. So 2 discernible steps, which means the intermediate has to exist for a brief amount of time, which means because it exists for a brief time, you can study it or identify it. So we can actually see spectroscopic evidence. We can use some sort of light interaction with this molecule to conclude that it was a carbocation. And generally speaking, the more R groups donating in, sorry, I did not mean to do that. The more R groups, carbon groups donating in, the more by the inductive effect they donate in, the more it can stabilize that plus charge, and the more likely it is to be that. So not only is tertiary going to be SN1 because it hinders how well the nucleophile comes in, it also helps stabilize the intermediate carbocation. So tertiary carbocation is more stable than secondary, which is more stable than primary. Okay, so we have that. And I want to put this in with a question mark because it doesn't fit here, but I always need to ask myself, is it a racemic mixture? So if this was a chiral center, you get half the time left, half the time right, so half the time R and half the time S. So if it was a chiral center, it would be a racemic mixture, 50-50 of each of the enantiomers. Okay, so time to look at this from a more visual perspective. Going to have something very similar to what we did, but this time, instead of visualizing something coming in and kicking this off, we actually visualize this coming off first and then the next group coming in. So initially, this electrophile is all that matters. Nucleophile is completely irrelevant. So if I follow the energy diagram, I'm going to actually do this. I'm going to go up, form a transition state before going down to a carbocation intermediate. So this is going to leave, so this bond is going to lengthen and become a dash bond, meaning it's not very strong. So they move over, In doing so, this gets a delta plus because it's starting to lose the electrons. This gets a delta minus because it's taking electrons. And we're going up, going up, going up, going up. I'm going to be somewhere in this neighborhood. Then, once we're there, it's going to keep on moving. So notice it moved on over and formed this carbocation. So it went from here back down to a stable sp2 hybridized intermediate. So I want to emphasize that that's sp2, even though it started at sp3. Okay, keeps on going. So now I can attack from either side. I chose attack from this side simply because I'm lazy in my animation and it took so long to make this that I decided to just cut and paste into the previous animation and move this in from this side. But note, it could go from left or it could go from right. So again, I'm choosing left just because I'm utterly lazy. I have my carbocation intermediate and I have this nucleophile, so it's going to come in this way. So here it goes, it comes in. And in doing so, used to have a full minus, now it's going to be a partial minus. This used to be a full plus, it's now going to be a partial plus because some of the electron density is starting to stabilize it. We're up around there somewhere, and then we're just going to keep on kicking in. So this is going to keep moving in a little bit more. This minus is going to completely disappear. This plus is going to disappear as electrons move all the way over. So it goes in, and we end up with this final product around here. So again, hopefully this is pretty straightforward. I only drew one of the two products, and because it's achiral, that was my reasoning. The other one would be the same thing, just rotated in space. So we only get one product, but if it was chiral, if this original molecule had 3 different R groups, then we'd get a racemic mixture. Okay, so what matters in this one? Well, the consider before, again, crowdedness. The more crowded it is, so notice now I do have a chiral center. I have an isopropyl group, a methyl, and an ethyl. So if you're going to do something with carbon and not have like another substituent, just a leaving group and all the rest is an alkane, in order to have a chiral group like this, you absolutely have to have at least 7 carbons, 3, 2, 1 on a central carbon. Okay, it's going to leave. So crowded electrophile, yes. Solvent has to absolutely positively favor carbocation formation, which means it must be protic. It has to be protic. If it is not, then it won't work. So let me say protic solvent. So it could be an alcohol, could be water, has to be something protic. During the reaction, you get a planar carbocation intermediate. It's 3 ligands, only 3 things attached. It's sp2 hybridized. And the key thing, because it's planar, you can attack from either side. Considering after, did it attack from the left side? Did it attack from the right side? So it could attack from this left side, and you end up something like this. Or it could attack from the right side, and you end up with something like this. So just doing my RNS, this is 1, 2, 3 with 4 in back. So I have my R product. This is 1, 2, 3 with 4 in back. So I have my S product. It is a racemic mixture, meaning it is half R, half S. Because there's only one chiral center, these are enantiomers. So racemic is specific for enantiomers. Hopefully one of the questions you're sitting there and pondering is, what if there's a second chiral center? Then it's no longer, we wouldn't call it racemic, because let's say the chiral center is here. The chiral center was here somehow. Then this chiral center would stay the same, this would change, so they would be diastereomers, and we call it a major-minor mixture. But racemic is if we get enantiomers. So I will get rid of my drawing, just say that one R is one is S. Rearrangement, interesting thought. Tertiary carbocations are very stable, not a big deal, but if you have a secondary carbocation, there's a chance that things can move. Hydrogen is lightest, so it's easiest to move, but rearrangement means, can something from another carbon move over? So could this H right here move its electrons over and I have an H here, leaving me with a tertiary carbocation? Sure. This adds a whole bunch of noise to what you end up getting. So anytime you have a carbocation, you have to worry about groups on the bench, on the carbon, being able to move around. So just like when the person left the bench first, everybody can move around before you were able to go and sit down. If this leaving group leaves before the nucleophile come in, these are free to move around. So you end up getting a much dirtier mixture. fast or slow, if you have to wait around, it's slow. It's going to take a while for the CL to leave. Once it leaves, you can do your thing, but you have to wait. So you're at the mercy of somebody else. Electrophile is all that matters in this case for the rate. Nucleophile is just sitting around waiting. Add more nucleophile, wouldn't matter at all because it's just going to wait that much longer. You're going to have that many more waiting around. Doesn't slow it down, doesn't speed it up, doesn't have any impact on it. So we're done for this one. This is SN1 and SN2. There's a lot here. If you need to, go back, watch things in slow motion, but make sure this clicks because this is the crux of everything when it comes to nucleophilic substitution. So thank you for taking part in this, and kind of exciting. Next podcast will be number 30. And again, I have no idea how many I'm going to have in the end, but we're not halfway yet, but we're getting close. So have an absolutely wonderful day, and I will see you at the next podcast. Bye.